we've decided to have a joint CEDAR GEM student-invited tutorial speaker. The speaker chosen this year is Anthea Koster from MIT Haystack Observatory, and she'll be talking about GPS.
All right, well, first I'd like to thank everybody for giving me the opportunity to talk about GPS. That's really been a lot of my career. And I'd also like to thank people, especially everybody at MIT Haystack Observatory. Without them, this talk wouldn't be here, and I'm very grateful for all their help along the years. I'd also like to recognize Jade Morton, who is a professor, and she gave me some wonderful view graphs here that I'm using. So, the way I have structured this talk, we're going to begin with the ABCs of GPS. I want every student in this room to leave with at least a basic understanding of what the measurements are and how they're made with GPS. Then we're going to talk a little bit about the history. This happens when you get old. You like to include history and things. So some of the history of measuring the ionosphere with GPS. I'm going to show a little bit about ionospheric and thermospheric coupling, even though I know the talk title says MI coupling, but I'll just briefly mention that. Then I'll focus on some of the new results that we're obtaining with GPS, combining GPS with other instruments. And finally, I'll give you, hopefully I have time to give you a brief sort of peek at what's on the horizon, what the students in this room should be aware of. So what is GPS? Well, it's a satellite constellation that was actually put together by the DoD, and its primary purpose was position, navigation, and timing. Now, it can only have, at most, 32 satellites, and that's because of the way the codes are structured. All right, right now, I think we have 30 or 31, so it's a pretty full constellation. We only need 24 to be fully operational. Okay, it has 6 orbital planes. There's 4 to 6 satellites per plane, and it's inclined at 55 degrees inclination. Keep that in the back of your mind. It does have something to do with our look angles in certain parts of the area. It's a near circular orbit. It's at 20,000 kilometers. That's almost half geosynchronous, so you see it twice a day. It's a little bit less than twice a day, but you know, typically if you're sitting there looking for him, you'll see him for about 4 hours, one particular satellite, and then about 12 hours later, you'll see the same satellite in the same position. Now, again, the most important thing about GPS is that each spacecraft has a very highly accurate atomic clock. In fact, I think they have 3 and they use a combination. But that is where everything comes from, the clock, the timing. So each satellite is also transmitting its clock information, and there are corrections that you have to apply because these atomic clocks drift a little bit, but they're still atomic, very, very precise. It also transmits information about its position, where it is, and you need that to actually figure out where you are. The signals are transmitted on 2, and nowadays we have some satellites that are transmitting on 3 frequencies for us to use. So what's the signal structure? First, every signal starts with, you know, your carrier phase. As I said, GPS for us has 2 or maybe 3, but the carrier phase, very important because that's where you get your precision. The phase is where we get our highly accurate data. Just remember that throughout the talk. From this, you can get Doppler information and you can get range, but to get anything except relative range, you're going to have to solve for that 2 pi ambiguity, and that's actually difficult, but there are techniques. Each satellite is code modulated, so that's why I said we only can have 32, because there are 32 distinct codes that are used. And the code that's being transmitted identifies the satellite. It's spread in power, and from that you can get range information. Now, on top of all of this, you have navigation data. Remember I said there's a navigation message. And in fact, this navigation message takes about 5 minutes. So when you first turn on your GPS after many, many hours of having it turned off, it may take a long time to acquire satellites. That's why it has to get the navigation data. and it actually gives you information about the satellite orbit, error correction, and the satellite health. So all of that's combined, and that's a GPS signal. So it's transmitted, that signal is transmitted at the satellite and at time TS. It's then received at the receiver at a later time. And from the difference between those two times, we calculate the pseudo range. That's using the code data. And with the phase data, we can calculate the carrier phase information. But remember I said there was that 2 pi or that ambiguity? That's what you have to solve for if you want accurate orbit information or range information from the phase data. So again, how does it work? This is just to give you a general situation. You have a receiver in your car on the ground. You're actually receiving up to, well, nowadays you can typically see 6 to 8, but you need to see 4 satellites to do a determination. You're getting the range or the range information to each of these satellites. So you have that time delta. So you have range to here, range to here, range to here. You also know where those satellites are. So if you put it into like a least squares calculation, you can determine what your range is. In addition, the reason you need 4 is you're calculating, remember your clock in your GPS receiver is not usually an atomic clock. And so you want to calculate a bias in time for that clock to bring it up to atomic accuracies. And that's why GPS has been such a great thing for all of us in the experimental community. When I was doing my PhD, I had to actually carry atomic clocks from Arecibo to St. Croix. Now you can just buy GPS receivers and get that same kind of information. So that's what this bias is, and that's why you need 4 satellites. Let me go back here. Now, in a perfect world, if we didn't have the atmosphere and we didn't have errors, this would work absolutely great. But there are always errors, and those errors, and I'm really only going to talk about the ionosphere, but the errors are the ephemera, so the GPS satellites really aren't giving you that great an orbit. They're giving you a pretty good, but not great orbit. The GPS clock has an error, so all of the clocks in the satellites themselves do have some errors. They do send error correction codes for them, but again, they're not as perfect as we would like. The receivers all have noise that they're adding to the data. Now that actually, this is pretty small, but it is something to consider. Multipath, and I'm going to show you what this is a problem, especially at low elevations. And then we have the atmosphere, and of course, that's what we care about, the ionosphere. So for us, the ionosphere is a measurement. For most GPS people, it is an error source. And I can also tell you, nowadays, the ionosphere is the largest single error source for GPS users. So I just want to show this about Multipath. Where you should never put your receiver is near a large metal structure. And so just remember, when you're actually putting your receiver out in the field, look around you. You want to have a clear view, and you don't want any large structures, because this is what your data is going to look like. So just remember. All right, for atmospheric propagation, you're a satellite, you're sending out a signal. You have to go through 2 layers of the atmosphere that are going to perturb your signal. The first is the ionosphere, and the second is the troposphere. The reason they perturb your signal is that each of these regions have their own indices of refraction. Now, the ionosphere has the one advantage that it's dispersive, so it's frequency dependent. And it was because of the ionosphere that the DoD designed GPS to have 2 frequencies. But most of us, if you have a GPS receiver in your car, you don't get that second frequency. You're just working on one. The troposphere is not frequency dependent, but to solve for this, you have to actually have all those other errors taken account of, and then you can solve for what the troposphere is doing. So again, what are the refraction effects that we care about? One is that your range information. You're calculating it as if it's traveling at the speed of light. It's not, it's traveling slower. So the observed range is actually larger than your true range. So you have to calculate for this ionospheric range correction. The other thing the signal does is it bends. All right, so there's a bending that's involved with the index of refraction changing as a function of altitude. This bending is used in all of the occultation measurements, and I'm going to briefly touch on that later. This observed range is how we get the TEC from all of our ground-based receivers. So this is even the complete total index of refraction in the ionosphere. This is the Appleton-Hartree equation. I've ignored collisions here, so if we added that, it would be a couple of terms longer. But for the majority of GPS processing, because the GPS signals are at L-band, so fairly high frequency, we can actually ignore this term here. All right, so these terms cancel out, but you should always remember that when we make our measurements, there is a little error that's introduced because we're ignoring all the magnetic field effects. So we're left with this 1 minus x times 1 minus x over 1 minus x. This cancels out. We're left with 1 minus x. X is the ratio of the plasma frequency over the carrier frequency. So, again, this is actually how you calculate your range correction. You make this assumption about the index of refraction, you're left with the term 1 minus a, where a is a constant, times the electron density over the frequency squared. And if you want to calculate for your range error for GPS, it's this equation right here. 40.3, this is in MKS units, by the way. 40.3, which is a constant, divided by the frequency squared, times the integral of the electron density from the ground all the way up to the satellite altitude. Now, because we have two frequencies, you can actually then calculate this for frequency 1 and frequency 2, take the difference, and back out what the TEC is. And so that's what we do to measure the TEC. We actually measure what the range error do the ionosphere is. We difference it because we have the two frequencies, and we calculate what TEC is. Now, just to give you a sense of how large this is, it's frequency dependent, so I have all these different frequencies. L-band is relatively high, and so if we have 50 TEC units, which actually for right now is still kind of a high number, but if you have 50 TEC units and you're looking straight up, you're going to have an error of about 12 meters. So just remember, if you're trying to land a plane, you don't want that kind of error. And it gets worse if you're actually looking at a lower elevation. There's something called a mapping function. So again, your TEC looking straight up is, say, 50, but as you go down in elevation, you're going through more TEC. So there is a mapping function. And just to give you kind of an idea, that mapping function typically varies between 1 and 3. And at 20 degrees elevation, it's about 2. You multiply that, and you're going to get an error of 26 meters. So, what are the ionospheric parameters that we get from GPS? For ground-based receivers, you calculate total electron content, and you can get some information about scintillation, S4 and sigma phi. And I'll go through that a little bit later. For space-based receivers, that's like cosmic, you can get electron density profiles, and you can get, again, some information about the scintillation. And this is what, let me get some coffee here. This is what the data looks like. It's for one satellite. Up here you have the code, that pseudo range. Notice it's kind of noisy. And this is a single satellite pass, so this is in hours. And it's actually from 0 to 6 hours. So I guess in this case you could see it for a long time. The carrier, or the phase data, is much more or less susceptible to multipath. And it's down here, very, very smooth. But you notice it starts at 0, and that's because we don't know exactly what the true range is. So what typically ionospheric scientists do is they use something called carrier-phased, now I can't even think of the word, carrier-phase smoothing. So we use this data and an average value of this to actually bring this up to here, and that's how we get our TEC. Now, this is my graphics, or my student's graphics, so it looks kind of silly, I know. But what I want to show you is, again, this mapping function. It is an error source. If we're looking straight up, it's not a problem. This is the path from the receiver to the satellite, no problem. But if you're looking along the line of sight to here, and you want to calculate what the vertical TEC is, and that's typically what we want to do, we actually have to use this mapping function. What we use may not be right because it kind of assumes that the ionosphere around your site is smooth and symmetric. Well, it's not, so that's the first place an error comes from. Then also, where do you assign this value? We typically pick a pierce point location to say this vertical TEC comes from this location. And that's because, you know, if we're looking along here, we're really sensing the ionosphere primarily along this path. But we may make an error in where we choose the pierce point location to be. So that's the first error source. The second one, and I think anybody in the GPS world will tell you that GPS biases are still a problem. And that's because your measurement is this delay between the two frequencies. Well, the delay is not just due to the ionosphere and the troposphere. That delay is due to receiver hardware and satellite hardware. The satellite biases are typically determined by the IGS community, and I think all of us agree that they're fairly stable. In our processing, we use the JPL biases. They're published online. I think that problem is relatively straightforward and solved. The receiver biases, however, are determined by the individual user, and most users estimate one bias over a 24-hour period. Well, the problem with that is that we actually have some evidence that this is true, these biases depend on temperature. I mean, think about it. Some of your delay biases are due to are introduced at the amplifier in the antenna, but they're also introduced in the cable length. And if that cable is, if you have a large gradient in temperature between day and night, it can introduce different delays between the two frequencies. So this is a problem, and this is why I will tell you that none of our TEC measurements are really better than 3 TEC, except that if you're looking at it in a relative sense, I think they're much better. So just remember that. I said I was going to tell you a little bit about what scintillation is. So again, we're a satellite, we're sending out a signal, but all of a sudden there are irregularities in the ionosphere. So you have an incident wave, it's got a uniform phase, uniform amplitude, it goes through this region, and the wave emerging from below the irregularities has now a non-uniform phase and a quasi-uniform, non-uniform amplitude. You receive it on the ground, and then there's a diffraction and interference pattern. All right, now to complicate this, you also have the problem that the irregularities are moving at a plasma drift speed, and the satellite's moving, okay? So you have both the movement of the satellite and the movement plasma drift. All right, but just again, to give you a sense of what is scintillation, this is actually made with Altair and it's at a lower frequency, but it gives you the idea. This is phase scintillation, and the axis is over here. We have a radius, and you can see there are certain places where we have up to almost 2 radians of variation in the phase. Again, at the bottom here is amplitude scintillation, and this is actually just noise, but as you get here into this region, you can see that the amplitude is varying quite a lot. Now, from that information, we can actually calculate parameters. One of them is S4, and it represents the amplitude scintillation. One of them is sigma phi, which represents or tells you something about what kind of phase scintillation is being observed. Again, for GPS, you're going to be telling people what this information is for L-band frequencies, and it's different for the different frequencies. I just want to show you some GPS results. They were collected by Ted Beach at AFRL, and I'm going to be showing you one of his earlier scintillation monitors later. So keep his name in mind. But they went to Ascension Island, which is right here, very close to the equator, and I think it is known to be one of the places in the world that sees the most scintillation. And here is just a as-L or plot of satellites in view, and I think they're tracking 8 satellites, or have I got that right? 8 satellites. Every place you see red there, they're measuring scintillation. And to give you again a sense of how much or what these parameters are that they're calculating, if you look at it, these are the individual satellites that they're tracking. This is the time in minutes, and any place there's a red, we can see what kind of phase information or phase we're seeing. And here is the S4 index. Again, this is the color code, this is the time, and these are the satellites. If you look at, say, this satellite here, which is PRN4, you can see we can have S4 measurements that are greater than 1. We know it, I think theoretically you only ever expect 1, but we know that you measure more than 1 sometimes because there's some focusing that goes on when you have large bubbles in which the irregularities are seen in. The phase fluctuation, again, they measure up to 2 radians of phase error. So basically we're saying that a lot of receivers would have trouble tracking in this kind of environment. Now I said I'd briefly mention GPS occultation because I'm sure at this conference you've heard about COSMIC and some of the other satellite programs that are making TEC measurements. Well, this is how they work. You have a LEO satellite. In this case, it was at about a little bit less than 800 kilometers, and it's here, and it's measuring the GPS signal. Now, as it is setting or rising, it's measuring it, it's bending, the signal is bending, and it's able to measure that bending to very, very high accuracy. So a typical occultation event for a LEO satellite in this kind of orbit is 1 to 2 minutes, and it begins with the signal path passing through the mesopause and ending with it grazing the Earth's limb. Okay, so again, the frequency, the way you measure this bending angle is, again, the phase, remember? And phase is very, very important. And so you can measure that to 1 part in 10 to the 13th, and that translates to a bending accuracy of about 1 microdegree. That's how they do it. They're measuring this change as you're going through. Now, it's the integrated effect of the bending caused by the atmosphere. So what you really want is a vertical profile. So they actually, it's kind of like an onion skin, if you think about it, and they have this Abel transform that actually, as you make this measurement at each point, and you attribute the additional bending to a different index of refraction. The problem with this is, if there are large gradients, you're assuming again that the ionosphere is fairly, the ionosphere is fairly constant over that area. And especially as you get to lower and lower elevations, you're going through more and more, further and further apart, and it's more likely that you're going to have some kind of, it's no longer spherically symmetric. And so that's a problem, and that's where a lot of the errors are introduced in these kind of measurements. But this is just actually when the cosmic constellation was full, and that's when it had 6 satellites. I think right now it's down to 5 operational satellites. It would see this many occultations in a day. Now, this is a little bit deceiving, I think, because, it's the green ones that are all the measurements. It's deceptive a little bit because it's not showing you what they're measuring hour to hour. We actually need a lot more coverage than this, hour to hour, to get the kind of data that at least I want. But as people may know, I really like data. So I'm giving you this address up here. This is where you can download the cosmic data. You can download TEC measurements. They're already doing that. And I'm giving you our database, which is where our TEC values are stored. We're not the only people who do this, but this is one place you can get TEC data, and we basically store vertical TEC in 1 degree by 1 degree bins where data exists. So we have a lot of gaps every 5 minutes. And currently, oh, this is wrong, sorry, we have data up to 2010 with a few days in 2011. So we've got a lot of data in there. We don't have everything yet. But if you want a particular day, just call us, we'll process it and get it online. So now we're in the second part. I hope you have some ABCs in your head. We're going to the history, or some of the history of measuring the ionosphere with GPS. And when I was putting this talk together, I realized I had enough material for at least a week of lectures, so I had to be kind of selective in what I said. This is the first GPS receiver I worked with. It was in 1985. This receiver cost MIT $150,000, and that was with the educational discount. And so that was a lot of money. It could only track 4 satellites at one time. Now, there were only 4 satellites up there then, and at that time, none of the none of the errors that the DoD introduces to the signal were there. They introduced 2 kinds of errors, or they did. One was called selective availability. That was turned off in 2000, and that's when everybody started to use GPS in their boats and everything. The second one, though, is still on, and I think a lot of people may not realize that. It's called anti-spoofing. Now, when they turned on anti-spoofing for us, we really could no longer make ionospheric measurements that were really worthwhile. So we had to get a new receiver, and receiver manufacturers were able to put their heads together and kind of reconstruct the second frequency. And that's how all of the scientific data that you're working with is gathered. They all kind of reconstruct this second frequency. Now, the problem is that the way they do that, you have a loss of about 13 dB in that second frequency, and it's almost impossible to track it if you're on a moving platform. Now, you can kind of see why the DoD wanted to do that. But with all the civilian use we are starting to get a second use of that second frequency and use of a third civil frequency. So that's kind of going away, but all the data that you're working with now is using this data from the L2 signal that is being reconstructed. Now, I also want to say that we were doing TEC measurements back in 1991. This is actually a TID that Patricia Dougherty and I measured when we were comparing data between Hanscom Air Force Base and Millstone Hill. And we actually saw a fairly large excursion in the TEC. Basically, we attributed it to a medium scale TID at night, and it had about a 3% perturbation of the TEC. Now, I'm showing this picture. This is Paul Kittner. He was one of the leaders in using GPS for ionospheric work. He passed away in October. But, so I'm doing this partly to honor him, but I'm also trying to show you that this is how a GPS scientist works. This is a chicken shack in Brazil. They put this plastic up here because the rain at times was coming in almost horizontally, and they had to protect the equipment. And in the back there is Brent Ledvina. Now, Paul actually developed one, I don't know if it was the first, but certainly it was one of the earliest GPS receivers that measured scintillation. And this was done by Ted Beach. I showed you some of his scintillation measurements earlier, and this actually, I think, was in, I could be wrong, 1996, 1995, but it's one of the earliest GPS scintillation receivers that are out there. I want to mention this because I think this has something to do with where we're going to go in the future. GPS science would not be where it is now without the IGS. The IGS and originally it was the International GPS Service, but it's changed to be the International GNSS Service. and that's because we're no longer the only game in town. GNSS stands for Global Navigation System Services, I think. But anyway, the IGS was kind of created by a group of scientists. They were primarily geodesists in 1989, and they basically got together and said, we're all going out and we're buying our own receivers, and we're having to do this complex orbit determination just to get the data we want. Why don't we band together and put out products so that we don't have to do these kind of calculations all of the time? So they did it. Now, this group was one of the very earliest users of the internet. Again, this kind of ages me. This is 1991, but the internet was just getting established. And you can imagine, they're exchanging large data sets worldwide. You can see why the internet was really important to get this project going. So the internet has really helped us here. But the thing that I think is most important about IGS is they stress the importance of standardized products. Products that, for example, I can actually get a Rhinex file. Now, it may not be the greatest way that you want it, but all receivers can be translated and put their data in a Rhinex file that any scientist in the world can understand. Prior to that, all the receivers were putting out their own binary files, and you needed different converters for all of this data. Now we have one standardized product. This was very important. They also made their data freely accessible on the internet, and that, again, is very critical. They did not design IGS for ionospheric physics. I don't even know they weren't thinking about that. They're thinking about plate motion and looking for earthquakes. So these two things are very important, and in the future, I think we need to think about that for all atmospheric data. So since its creation, the IGS Central Bureau is operated by Ruth Nealon. She's at JPL, and it's really an interdisciplinary service in support of earth sciences and society. Science, from measuring the height of the ocean, all sorts of science has been enabled by this institution. So yeah, I want to, again, emphasize that. So back in 1992, we only had 20. The IGS was working on 20 geodetic receivers, and they were distributed worldwide. The reason you need them worldwide is they were trying to improve the GPS orbits. Remember, to actually calculate your position, you need information about where the satellite is. Well, the DoD only gives you so much accuracy. They wanted more, so they had to do their own orbit determination, and so you needed this global distribution. Now, in 2007, I'm sure this number has increased. There are over 400. Now, that's not all the receivers that I use, but these receivers are all high-quality receivers. They're mounted in a particular way. You can trust the data from the IGS network. And based on this data, and I want to give credit to JPL where it's deserved, scientists at JPL, that was Brian Wilson and Tony Monucci, first developed mapping of the TEC across the US. So that was the beginning. So nowadays we have, or I use, probably close to 3,000 GPS receivers. So the growth of scientific receivers and data available on the web has been exponential since 2000. But by combining data from all of these different networks, you have what's called a distributed network, and it basically allows you to get global physics that was unattainable with a single measurement. And just an example are these kind of movies where we were enabled to see things, features like SED moving across the US. So how did I start doing this? Well, back in 2000, I was actually working at Lincoln Lab in the satellite tracking program, and we were using GPS to try and improve our orbit. So we were trying to get better estimates of what that range delay was. So I was actually responsible for a very high-quality receiver at Millstone and one in Florida. And all of a sudden, on this Bastille Day storm, we had the largest solar flare we had had in 9 years. And I thought, well, I should look at the data and see what was happening. And I did, and it turned out, and I actually attribute this to loss of signal on L2. I don't know. This is the only time it happened while I was there, but there were 4 hours where we were not able to track, 4 hours. And I went right across the road and said, Phil, what was going on at Millstone Hill? And he said, well, we were tracking that was a storm. We were measuring very, very large vertical westward drifts above Millstone, which corresponds to a high electric field. So it was during these conditions that we were not able to track. So then I talked to Jon Foster, and he said, well, go get some more data. Go see what the other things happened. And again, this was all of the data I could gather from around New England. Most, but not all of the receivers had trouble tracking through this storm. There did appear to be one in Portland. It may have been a different kind of receiver that tracked, but then I went and I gathered the data from Florida, and this is what I saw. I saw, and I should say prior to 2100, it was tracking this kind of TEC shape. This is actually the TEC, this is in hours, and the storm started sometime around here. And as you can see, their measurements, which were on the order of 40, 50, went up to over 160 TEC. I mean, it was almost unbelievable. So we're going, all right, what's happening? And again, this was kind of at the prodding of Jon Foster. He said, collect all the data you can, which of course in those days was maybe 300 receivers. He said, let's look at what we see. And this is the first map that we had of storm enhanced density, where you can see in Florida, we have this plume of ionization where the TEC was 185. So we were like, oh my gosh. Now, when I first showed this at one of the IES conferences, or a conference, Beacon Satellite Symposium, some of the old timers got up and said, we would have seen this. This is not real. This is your receiver biases. And we were saying, no, we think this is real. So I had to go back and look at all the other storms. And it turned out that this feature happens all the time if you have a storm that occurs between 1600 and 2100 over the US. That's UT. So this feature, as you can see, here's a storm, and here's the famous November 20th storm. It happens all the time. Now, Jon Foster had some hint of this because I think it was in 1993, he had collected a lot of Millstone Hill incoherent scatter measurements, and he had seen a feature similar to this. So that was why he thought something like this was going on before. But GPS was the first, by combining all the GPS data, this was how we were able to make these measurements. Now this is from Tony Monucci. It's also kind of a famous slide. This is I think Jason or Topex, and I may be wrong, but they were measuring TEC up to about 800 kilometers. And these are the 3 orbits. The blue is this one here, and it's the earliest. And again, this is magnetic latitude and vertical TEC estimate. So blue is before the storm, right? You see here are the 2 peaks of the equatorial anomaly. Then we have the red storm, which is I think when the storm actually started to happen. Again, you can see this huge increase in TEC, a dip in the TEC at equatorial latitudes, and again, a huge increase. And then finally, by 2200 UT, this is the black orbit, you can see this. Again, TEC's measured up over 300 TEC units, which is huge, and we can't even really measure TEC below that. Now, what you should observe here is that you see a decrease in the equator, and you see these huge increases, but they're actually further north and further south. So the equatorial anomaly has expanded, all right? Now, this Jon Foster explained with penetration electric fields, and I don't know if I can go back here, let's see. Start here, this was prior to, or an electric field is just starting, I guess this is going kind of fast. It pushes the plasma up. Then we have a hole that's forming in the equatorial region. And we have this increased plasma in the mid-latitudes. Then we have something called the subaraural polarization stream. It's an electric field that is northward or southward, depending on what. And it's pushing the plasma out over here, and that's what's just causing the plume that we see over the US. And so this is a plume. We also, or John also noticed that this was correlated with the drainage plume that people were measuring with the image satellite. Now, the image satellite was, I think, at an orbit of about 8 Earth radii, and it was measuring the plasmaspheric content. And they noticed during storms that you would see this tail of ionization kind of flowing out. And basically, if you map this to the equatorial boundary or projection, you can see that our plume maps one-to-one with this plume that they were observing from space. And I like this. This actually is a movie showing you an SED. It's from a storm in 2001, April 12th and 11th. And basically, it shows you the plasmasphere before the storm and then after. And you'll notice it's decreased quite a lot. And you have this plume of ionization that correlates with this SED plume that we have. So it's kind of showing you how the plasmasphere is sort of draining out. What we're seeing here on the ground is kind of the base of the plume. It's the footprint in the ionosphere. What they're seeing out here is on top, it's the plasmasphere emptying out. But both of these are being pushed by that subaraural electric field. And this is from Jerry Goldstein. That SAPS channel is related to changes in the ring current. This is a merged figure, but you can see that here's the enhancement of the ring current, and it sits right on the edge of where that plume is. All right, this actually, that was all part of our history. I want to show you what's next. But before doing it, I want to show you a little bit about some of the work we're doing, in ionospheric-thermospheric coupling, which I think is pretty exciting. These are TIDs that are observed over Japan. Many people have seen them. I think at this conference, you've probably seen some great pictures of the earthquake and the tsunami that over Japan. But basically, this just confirms that what they're seeing here is real. This was the same TEC as imaged by airglow. Remember, a lot of times when we first make these measurements, people don't believe us, and so you have to find other instruments that are seeing the same things. Now, this data, and I think people should be aware of it, is available at this website. This was from Takuya Sugoya. He was a postdoc at Millstone, or a Japanese fellow at Millstone for quite a while, and he developed this software which allows you to download data. I think it's up to 2010, but you can always email Talk and he will do more. And you can look at these plots. I think they're every 20 minutes. So if you think there may be a TID over the US, go to this website and look. And finally, this is what I would say this is associated with a geomagnetic storm. This is a very large scale TID that we're observing. Now, the following movie is to show that people have been concerned with the stratosphere for a long time. And hopefully it will start. Oh, well, sorry, it gets the hit. So this actually is one of the early movies which had Leonard Nimoy. So I thought it would kind of wake everybody up. Larissa and Shungrong and Koki Chow and Bella Fair, a lot of people, and myself included, have been really looking at what is the ionospheric signature of stratospheric warming. Stratospheric warming is one of the very, very large increases in temperature over the stratosphere in the north. This is in the North Pole at about 30 kilometers. This actually occurs on January 23rd, and we have a big change in the winds. Nobody really thought that we would see anything in the equatorial region, and Koki Chow at Hikamarka saw that the drift pattern changed quite a bit from morning to afternoon. And so we then went and said, okay, let's look at the TEC data and see if we see any changes due to the changes in the drift. And this is actually from before we had the stratospheric warming, and this is during. And this is a morning effect. So the morning ionosphere TEC was increased by a factor of 50 to 100% in the morning. And we were able to observe this with the TEC data. So now I want to show you some of the new work. I'll do this really quickly of the MI coupling with GPS. This actually, I think it's really cool. This was done with the image satellite, but it was using from the University of Massachusetts at Lowell. It's called RPI, Radio Plasma Imager. And basically, they picked a time where we have an SED plume over the pole, and they were looking at their different models and then their measurements of the electron density at an altitude of 4.5 to 6.07 Earth radii. And they saw very, very, very large increases right at the same time we were observing this structure over the pole. So I think it's pretty exciting how these things tie up. All right. Now this actually is from Shasha Zhao. I think this paper has just been published, so you can get it, but it's not really, I think it's one of the just accepted papers in GRL. And you can see this is monitoring what the TEC does during a substorm. And basically this is before the onset of a substorm. This is the mid-latitude trough. Right after the substorm, you can see it goes a little bit further south. And then in the late expansion phase, it actually starts to fill in, and we have a narrowing of the mid-latitude trough. Here she's actually looking at one particular longitude sector. I think it's over Alaska, and she's looking at it as a function of time, UT. So this is actually 2 days. That's why you see this peak. This is on the disturbed day. This is on a quiet day, and you can see this filling right at the substorm onset. And this is magnetic latitude. So you can see we have this big trough, and then all of a sudden this is filled in, and then this is normal. Now, the other people who are doing really great stuff right now is SuperDarn. They have this new SuperDarn network that's monitoring the mid-latitudes. And we had an SED, very small one, because we're still climbing out of the solar minimum. But we had an SED on February 4th, and you can see it's right here. Evan Thomas actually then took the data from what the SuperDarn was observing, and you can see they're seeing irregularities right there in the plume. The next one, again, is a SAPS event. This is by Al Clausen at Virginia Tech. And here you can see, this is much later in the morning, we can see a deep hole right here. And here they've overfilled it with, again, observation. This is the SAPS channel, and here we see observations from the mid-latitude SuperDarn. And you can see this polar crossing. This is basically observing the precipitation. So we know right here, it's from Pose, I think. You can see that this is the edge of the auroral region right here. So this is really the trough region where we're seeing these observations. Now, again, there's a lot of work being done with ionospheric tomography that's, I think, exciting, and I think we have a lot to go. This is from Endawaki Yitzengao and I think Mark Muldwin, where they're actually seeing some ion outflow or using some of their tomography schemes. This is tomography done by Gary Buss looking at the equatorial ionosphere, and this is Catherine Mitchell's famous picture. But I think this is a growing field, ionospheric tomography. So what's on the horizon? Very quickly, you want me to stop? We got more signals coming up. So the satellites are being launched. They have an additional civilian signal on L2, and they have this new third frequency that I think there's 2 satellites now. I have not worked with any of this data, but I'm hoping that people will start using it for ionospheric research. The other thing is we're not the only game in town. And again, I'm pretty much strictly a GPS person, but I have done some work with GLONASS before. GLONASS kind of faded away in about 1997, and now it's coming back up. It has a big an advantage over GPS because it's at a higher inclination, and so it can actually sense a lot more of the auroral zone. You can measure the ionosphere with GLONASS. We have ESA, we have Galileo, and China is starting to launch their compass satellite. There's 2 up there. Again, I just want to say with all of the low software receivers are being developed, and with these new signals, we're able to get low-cost, low-power measurements. I really want to put some of these sensors out at sea. Why? Because I'd like to fill in these gaps. Now, this I think is really exciting. It's from David, Muir, Susan Scone. They had a GPS workshop here, and I was amazed. This is actually magnetic perturbations. That's the blue, and the red is TEC. And you can see there's a strong correlation. And again, this is from David. We can see here's a time where they saw some pulsations. They look at a Doppler sounder. They saw pulsations, and again, they saw it with magnetometer, so we know something's going on. We see this correlation between, this is, I think, a magnetometer here. No, this is the satellite TEC, and this is the magnetometer data. So GPS is measuring these ULF waves, and this is it. Finally, sorry. So in this last decade, I'd say global GPS TEC maps have really provided a paradigm shift in the way we study the ionosphere, troposphere, magnetosphere, plasmasphere. GPS has played a key role in our system science studies, and I really believe that we're at the dawn of a new age, and we need graduate students to start using all this data, helping us move towards the future. Okay, a lot of new discoveries are out there. I'm done, sorry, and I'm over time.
Thank you, Anthea.